Section 15.2, Fundamentals of Probability. We're going to start off with the meaning of probability. The probability of an outcome from a random experiment is the relative frequency of the outcome if the experiment were run a large number of times. So the relative frequency if the experiment were run a large number of times. So for example, let's determine the probability of each of the following. So the first one, part A, if you flip a fair coin, what is the probability of heads? So we're going to be doing what we call theoretical probability here, and that's one where you assume all the possibilities are equally likely, which on a fair coin would be the case. And what you want to do is start off thinking about how many things are possible when you flip a fair coin. And on standard fair coin, there's two sides, so there's two possibilities. And then for the numerator of this fraction, you want to think how many of those sides are heads, and on a standard fair coin, that would just be one of them. So the standard thing that we think about calculating when somebody says calculate a probability is we're going to think that through in a fraction. So that fraction represents the probability, 1/2. But it's common to change that to a decimal. So if you do 1 divided by 2, you will get 0.5. And if you thought of that as a percentage, moving the decimal over 2 spots, then you would have 50%. So I always think of probability as having these kind of three representations. We think about it and we kind of work it out using fractions. We tend to write it as a decimal, and then we usually say it to somebody as a percentage. So if somebody asks me what's the probability that a fair coin would be heads, it's common that I'd say there's a 50% chance of that. So let's look at another example. If you rolled a balanced die, what is the probability that will show up with a 3 on top? So if we're talking about the standard die, then we've got 6 sides to that. So we start off with the denominator and say we've got 6 possibilities, and then we think about how many of those would show the number 3 on top, which there it happens to be. And if it's a standard die, that's only going to be on one of the different sides, so that would be 1/6. And then I'm going to go to a decimal on that too, but with 1/6, unlike a half, it doesn't work out nice as a decimal. So if I do 1 divided by 6, I get this repeating decimal. So I would round that usually to 4 decimal places is what I like to do. So 0.1667, because I'm rounding it, I'd say that's an approximation. And then I would say in percentage form, that would be 16.67%. All right, so just talking about a couple things here. I like to write probabilities in decimals and only say the percentages, but when you're doing homework, you need to do whatever my math lab asks you to do. So if it says to write it as a percentage, do that. If it says write it as a reduced fraction, do that. But the standard is to think in fractions, write decimals, and say percentages. And then one other note up here, it said that we think of probability as the long-term relative frequency if the experiment were run a large number of times. So what we're saying here is if you flip a coin that's fair over and over again, then in the long run, 50% of the tosses will be heads. If you rolled a fair balanced die, like I believe this one to be, over and over and over again, then in the long run, you should end up with 16.67% threes, just like that. All right, so moving on. The sample space of a random experiment is the group of all possible outcomes. So you're thinking about what is everything that could happen. If we were to list the sample space for this die, we might say that the sample space was the set of numbers 1, 2, 3, 4, 5, 6, because that's everything that could show up on this die. Okay? An event is sum of the outcomes in the sample space. It could be as many as all or as little as none of the outcomes. So if I ask something like on a die, what's the probability that you get a number that is less than 8? That would be all 6 of the sides. If I said what's the probability that you get a number, that the number 9 shows up, that's going to be 0, because none of the sides on the standard fair die have a 9 on them. All right, if I said what's the probability it's odd, then there's 3 things that could happen, the 1, the 3, or the 5. So you could have 1 thing, 3 things, all the things, none of the things. Those would all be considered events. So what we've been doing here is calculating theoretical probabilities. That's one that applies when all of the possibilities are equally likely to occur. And when you do that, you think it through in fractions f over n, where n is the total number of possible simple outcomes, and f is the number of ways the event can occur. So just a brief discussion of what it means to be a simple outcome. A simple outcome is one that can only occur one way. So we were talking about the number 3 on the die earlier. That's a simple outcome because there's only one side on this die that has the 3 on it. But if I said something like the probability that the die comes up even, that's not simple because that could be a 6, that could be a 4, that could be a 2. So simple outcome only would be satisfied by one of the possibilities, and other types of events have multiple outcomes in them. All right, one more example to finish off this page. A jar contains a total of 884 marbles made up of a mixture of red, white, and blue. The frequencies for the colors are shown in the table below. Suppose one marble is selected at random. Determine the probability that the marble selected is white. All right, so this is very similar. We want to think about the probability of white. Here's some notation we might use for that. And we want to think about this f over n style, where the denominator is how many things are possible. Sometimes people will say 3 because they're thinking red, white, and blue are the different colors in there. But we're not randomly selecting a color, we're randomly selecting a marble. So how many marbles are there? 884. So if they said we were going to randomly select a color, you could put a 3 down there, but we're randomly selecting a marble, so it's the total number of marbles. And then the numerator would be how many of those marbles are white. And in this particular jar, it looks like we've got 289 of those. So that would be the probability. Maybe that reduces, maybe it wouldn't. In statistics, we generally do not reduce our probabilities. We just go to a decimal. So I bring in the calculator and say 289 out of 884. And that probability is 0.3269, at least approximately. So a couple things. I like to round these to 4 decimals. That's my standard. That's what I do in statistics all the time. But if my math lab tells you to use 3 or 5 or 2 or whatever, then you should do what they say. I never reduce my fractions. I always go to a decimal. But if my math lab asks you for a reduced fraction, then you will have to do that. All right. Let's move on to another one. What's the probability that the marble is not blue? And we just go ahead and add the structure right there. So what's the probability that you don't get a blue marble? Well, there's 2 ways that you can handle that. One of them, you could think, all right, what kind of marbles are not blue? Red ones and white ones. So there's 351 red ones plus 289 white ones out of 884 marbles, and that would be a perfectly okay way to do that. However, there's another option, which is instead of thinking about what kind of marbles there are besides blue, you could just say there's 884 marbles in the jar and I don't want the blue ones, so I'm going to subtract those away, and then whatever's left is not blue, and I would divide by 884. And either of those should give you the same answer. Hopefully if you thought about this before I started working on it, you did it the subtraction way. They both work, but think about this. What if this jar had 19 different colors of marbles in it, and you were asked what's the probability that the one you get is not blue? Do you really want to add up the 18 different totals for the other colors, or would you rather just subtract the blue away from the total? So it's good to be thinking subtraction sometimes. It can be faster. And then let me just go ahead and point out that it really doesn't matter which of those you do, though I will point out on the calculator to make this work right, because there's an addition in the top or a subtraction, you need to put parentheses around that in the calculator. You don't really need to write them down, but they need to be in the calculator. So there's the 351 plus 289 divided by 884. So the answer to this problem is approximately 0.72. It's a 39, but followed by an 8. So think of that as a 39 that we're rounding up, and that would become 40. And then let me just show you what happens if you forget the parentheses. You get this, which actually just doesn't make sense at all as a probability. Probabilities always need to be between 0 and 1 inclusive. It can be as small as 0, as big as 1, but it can't be 351. So hopefully if you forgot parentheses, when you got a weird answer like that, you would notice. And let me just show you that the other way works too. 884 minus 244 divided by 884 exact same answer that we got up there, 0.7240 with rounding. All right, let's move on to the last one. What's the probability that you'd get a purple marble? So the key thing is, what's the probability that if you randomly select a marble from this jar that you'd get a purple one? Well, let me separate this out a little bit. Out of the 884 marbles that are in this jar, 0 of them are purple. So the probability would be 0. So that's what we call an impossible event. Not that it's impossible to get a purple marble in this world, I've seen them, but you're not going to get one out of this jar. So determine the probability of each of the following. What is the probability that a randomly selected person from Chabot will have been born on a Sunday? So we're going to approach this using theoretical probability. So we're going to start off with a fraction, and in the denominator of that fraction we're going to think about what are all the possible days somebody could be born on, and there's 7 different days for that. And then we're interested specifically in a Sunday, so that would be 1/7 of the possibilities. And then we would want to go to a decimal on that, so we'll go to the calculator. So I'll bring in the calculator for that. We do the 1 divided by 7, and we get 0.1429. And we'd probably say that as there's a 14.29% chance that a randomly selected person from Chabot would have been born on a Sunday. And that would be our theoretical answer. One thing I will point out is that makes the assumption that all 7 of those days are equally likely to be a day that somebody's born on. If that's not true, we might do a different approach called empirical probability, and we'll be looking at that a little bit further down the page. When you see these on my math lab, they want you to do them from the theoretical approach that all of those days are equally likely. All right, so moving on to the next one. What is the probability that the spinner shown below will land on the number 3? So here I'm assuming if we took that red dial and we spun it, that it would be equally likely to stop anywhere on the wheel. And there's maybe a bit of a temptation to say, well, how many ways could it turn out? 1, 2, 3, 4, and make a denominator of 4. But you really need that equally likely part for the theoretical to work out, and it seems like the spinner would be more likely to land in the 4 than the 1 because there's more space, and even more likely to land in the 3. So when I'm thinking about the probability, what I want there is all of this portion that is the 3. And there's a couple ways to look at it. One is just visually, how much of the circle is that? And I think if you look at that, you'd see that that's 1/2. Another way you could do it is take the lines that are already drawn and extend those out. And then extend this one out. And make a similar line like this one this way. And I think if we do that, then we have the spinner broken up into equal parts. And there's 8 of them. So the spinner is equally likely to land in any of those 8 parts. But how many of them would be in the region numbered as 3 that we have shaded? 1, 2, 3, 4 of them. So it'd be 4/8, which does reduce to 1/2, which we could go to a decimal and say that's 0.5 or 50%. And I think the 1/2 makes sense with what we saw at first. Half of the places that the spinner could land are labeled as 3. But if you want to do it from a counting point of view, then you need to make sure the pieces that you're counting are all equal size. So kind of drawing those lines, kind of a common denominator thing in a way, but just doing it visually. All right, let's move on to the next one. What is the probability that the sum resulting from rolling 2 fair dice would be a 7? So this question's a little tougher than than you might think at first. And one of the things I would point out is a pretty popular casino game would be the game of craps. And they roll 2 dice in that game and look at the sum, and 7 is kind of the most important game in that, the most important number in that game. Lots of people play that. Maybe you've played it before. So I would encourage you to pause the video and see if you can answer this question on your own. It is a little tricky, but give it a try. See if you can figure it out. And then once you've got a try, go ahead and resume the video and I'll show you my approach. All right, so I think the thing that's tricky about answering this question is it's really hard to imagine the equally likely possibilities in your head. Like on this one, we drew them. Here, there was 7 days, so it's kind of easy to think about. This one's tougher. So something that you would want to do, and space a little tight for this, but I think you want to list every possibility that could happen on each of the 2 dice and then think about all the sums. And you don't want to just think about it, you want to show yourself so you can do the counting that you need to easier. This doesn't have to be the case, but I'm going to pretend one of the dice is purple and the other one is green. So on the purple die, you could get a 1, a 2, a 3, a 4, a 5, or a 6. And then on the green die, you could get a 1, a 2, a 3, a 4, a 5, or a 6. And then I'm going to think about all the different sums that we could get when we look at those combinations. So if you rolled a 1 on the purple die, then if you rolled a 1 on the green die to go with that, your sum would be 2. But if the green die was a 2, your sum would be 3, or we could get a 4, 5, 6, or 7. If we rolled a 1 on the purple and a 6 on the green, sum would be 7. If we rolled a 2 on the purple and then thought about all those combinations with the green, they would all be 1 higher. The 2 with the 1 would now be a 3, get a 4, 5, 6, 7, and because a 2 with a 6 would add up to 8, that's our last one there. And then every time the number on the purple die goes up 1, the possible sums go up. So this would be 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, and then finally 7, 8, 9, 10, 11, and 12. And there's a pattern to that, and I definitely filled it in using that pattern, but you want to make sure that it makes sense to you, not just from a pattern point of view. So like, why is that a 10? Not just because it was after 9 and before 11, but because it was a 6 on the purple die and a 4 on the green die, and the 6 plus 4 gives us that 10. Sometimes people object to the idea that I have a 2 with a 3 making this 5, but I listed 2 with a 3 again for a 5, because they're saying that's just the same thing. That's where thinking of these as different colors is handy, because it's different to have a purple 2 with a green 3 than a green 2 with a purple 3. Even though the sum is the same, those are different faces showing on the dice. So when you look at how many possibilities there are for our denominator of the probability the sum would be a 7, you look at all the different sums that could happen, not just like different values, but all the ways they could happen. So you have 1, 2, 3, 4, 5, 6 times 6 rows. So there's 36 different combinations of a purple number and a green number. So 36 is our denominator, and then we would say how many of those resulted in us getting a 7. So 1, 2, 3, 4, 5, 6. So the probability would be 6 out of 36. Sometimes my math lab insists on you reducing those, sometimes not. So if you need to reduce it, you could cancel a 6. Most of the time we're happy to just go to a decimal without reducing. So 6 over 36 is approximately 0.1667. And if somebody was asking me the probability and I was saying the answer, I'd say 16.67%. So you're going to see that come up every once in a while, this probability question about rolling 2 dice and looking at different sums. I would suggest every time you hear that, you take a moment to write out the full sample space for that, listing every possible combination of numbers on the 2 dice. So a chart like this is really helpful for that. All right, so there's another method of probability besides theoretical, which is empirical. And empirical probability, we say if we run a random experiment a large number of times, then we can use the relative frequency as an estimate of the actual probability. And that's good to do when you have a hard time figuring out what all the equally likely possibilities are. I would argue that would probably be a better idea for this question about the probability of someone being born on a Sunday. If it was all just up to nature and, when did the time come, I think maybe every day would be equally likely. But sometimes for medical reasons, a woman might have to schedule a C-section to have her baby. And if you think about that, maybe the doctor's not so likely to schedule that for a Sunday. So maybe a Monday or a Tuesday might be a day more likely for babies to be born, because when the doctor is involved in choosing the day, maybe they're less likely to pick a Sunday. So empirical probability would say the approach to answering that would be to just look at a large number of birth records and see what percentage of babies are born on Sundays and use that as an estimate for the actual probability. So let me show you a few examples where we take that approach. What's the probability that a baseball player with a .300 batting average, what's the probability of them getting a hit in their next at bat? So usually in baseball we'd refer to that as a 300 batting average. They don't tend to say the decimal. But what that number is just a relative frequency where the numerator is the number of hits and the denominator is the official number of at-bats. So this is a relative frequency for the person getting a hit, and that relative frequency could be used as an estimate of the actual probability. So I would say the probability that that person would get a hit in their next at bat is just 0.300. So that relative frequency just becomes my probability. Maybe it would make sense to put the approximately equal there because I know since I'm using a number from a sample, it's just an estimate. But that would be my best estimate of their chance of getting a hit, is looking at their past performance and what was the relative frequency. That can come a little bit different, but this is still very similar. During the 2015-2016 NBA season, Stephen Curry for the Golden State Warriors, World Championship Golden State Warriors, made 402 out of 886 three-point shot attempts. So based on this, what's the probability that he would make his next three-point attempt? So assuming that shot came at some point in time right after we had collected this data, our best estimate of the probability of him making a three-pointer, our best estimate of that would come from the relative frequency. So how many of those did he take in our data set? 886. How many of them did he make? 402. So what is the relative frequency? 402 divided by 886, which is about 0.4537. So then I'd say there's about a 45.37% chance that he would make his next three-point shot. So that's how empirical probability works. We're not just thinking like what could happen. If you think of the possibilities, he could make a shot or he could miss a shot. So you might think it's 50-50. But you know, some players are more likely to make that shot than others, Steph being one of the better three-point shooters. But how do you figure it out? It's not just by make or miss. You have to think about how good they are at it, and the only way to really start figuring that out is to look at what they've done in the past, and that provides an estimate for their true probability. And then a follow-up to that, if you were to look at his next 87 shots, how many do you think he would make? Well, what you need to remember there is that probability is an estimate of future relative frequencies as well. So if in the past he's made 45.37%, or if the probability is 45.37%, then we would estimate that he would make about 45.37% of his next 87 shots. So what we do there is we take the 87 tries and we multiply that by the probability of a make, 0.4537. And then we're doing 45.37% of, or times, 87 shots and looking to see how that comes out. So taking the 0.4537 times 87, I'd change the order there, but order doesn't matter on multiplication. We'd say that's going to be about 39.47 made three-pointers. There's a couple things you could do there. You could take that number and say, well, it doesn't make sense to say he's going to make a decimal number of 3, so I'll change that to about 39. But you'll find out later in statistics we consider this to be sort of an average, and even when the result can only be a whole number, it still makes sense to talk about the average as a decimal. That's still possible. So you don't have to change that to a whole number, but that would be a reasonable thing to do as well. I'd just go ahead and leave it like this, and I would use in my answer the word about, because there's no way he's going to make that many exactly. So I would say he'll probably make about 39.47 of them, meaning it'll be nearby. Maybe it's 38 or 39 or 40 or 41. Those are all reasonably close to that. And it is, after all, a random sort of experiment, so we wouldn't expect it to come out just as the probability estimated anyways. From game to game, he'll have different level of performance. All right, continuing on, let's go ahead and look at some properties of probability. and then we will also do some more examples. So the probability of an impossible event is equal to 0. So that's the lowest probability you can ever get for a probability question. If it's absolutely impossible the event could happen, the probability would be 0. For a sure event, the probability is equal to 1, and that's the highest probability that you can ever get for an event. So probability of any event is somewhere between 0 and 1, inclusive. Inclusive means the endpoints are included in that conversation. So we're saying 0 and 1 are possible answers, or anything in between. So any probability question has to have an answer in that range. If you get a negative answer, it's wrong. If you get 1 point something or anything bigger than that, it's wrong. Probability has to be between 0 and 1. So think about that when you get answers, and if you ever get something negative or bigger than 1, you know it's wrong, so go back and look at your work and see if you can figure out what went wrong. And then the last one, the sum of the probabilities of all the single outcome or simple events in a sample space is equal to 1. So if you think of all the simple things that could happen, things that only happen one way, you could find all those probabilities and add them all up, and the total probability should equal 1. All right, and we can take advantage of that sometimes when we choose to use subtraction, and we'll see some of that as we move forward. So let's look at an example. 1,467 randomly selected adults were selected and asked how many times per week they visit quick service restaurants. Use the pie chart of the results to answer the following questions. So we have this pie chart. You can look at the colors to kind of match things up here. Less than once a week, 17.67% is this blue wedge. And you could look at it just to make sure that they kind of match up, but we'll end up answering everything just from these percentages. But notice the biggest percentages are the biggest slices of the pie. So we have, looks like once a week is the biggest answer. And then this green wedge, which looks like a little bit less than a fourth, is the next biggest answer. And notice when we look that one up for twice a week, it is a little less than a fourth, or 25%. But you can just look at the numbers as we answer the questions. That's what we'll end up doing more than looking at the size of the pie wedges, but they should match up. So find the probability that a randomly selected person from this survey group of these 1,467 people visits quick service restaurants more than 4 times a week. So I would argue that what they're listing over here is the relative frequency, but the relative frequency is also our probability. It's the same calculation. This is how many people were like that divided by the 1,467. So somebody's just done that division work for us already. So I would say the probability of more than 4 is equal to that 6.7%, but I would say keep in mind we usually write probability in decimal form, so if we move the decimal 2 spots to the left and got rid of the percentage symbol, that would be the standard way to write that probability. So the probability answer is essentially just sitting there for us, and our job is to write it in the normal probability way, which would be decimal format instead of percent. Let's look at a couple more. Find the probability that a randomly selected person from that survey group visits quick service restaurants less than twice a week. So let's see, less than twice a week is not directly listed here, but I would argue that it's these combined, because if it's only once a week, that's definitely less than twice. If it was less than once, that's also less than twice. But if it was twice, that is not less than, and certainly not 3, 4, or more. So it's those two categories. So I would add them up, 17.6% plus 31.7%. And let's see, a little bit of, not too bad, a little messy. I'll bring in the calculator. 17.6 plus 31.7. Let's see, 13, carry the 1, 9. Should be 49.3, let's see. Yeah, make sure to keep the brain sharp. Try and do it in my head, even if I am using the calculator. And then I would just say, because of the probability, we should probably write it in decimal form at the end. So 0.493. So if they give you a word description and it's more than one of the categories there, then just add those percentages together. We'll talk about that a little more as we continue on in the packet. And then the last one for this pie chart, find the probability that a randomly selected person from the survey group visits quick service restaurants at least once a week. So at least once a week. So that would be once or more, right? So that would be once a week or more. So that would be all this stuff that is kind of circled in purple. I don't know about circle, got a corner on it. But anyways, right? That's what we're talking about. So there's two approaches you could use. One of them would be like we just did. There's 1, 2, 3, 4, 5 categories that meet the description. Just add them up. But the other thing we could do is, since there's only one we don't want, is we could subtract. And I think that would be a better approach. So I could say, let's see, the total of all that is 100%. And I want all of that except for the less than 1 week. So if I got rid of that 17.6% from that group, that should be what I'd get if I added all those other ones together. And doing that subtraction, I believe, would be 82.4%. So I think that's a better approach than adding all those up. That's a really key thing in statistics, is to remember that adding is one way to get there, but you can also subtract what you don't want. We're going to formalize that as a rule in a little bit, but it's definitely something to be thinking about already. And then since we did this with all the other ones, we should probably change that to 0.824, write it in as a decimal, because that's typically what we do for probability. Just going to drag the calculator in here real quick and double check that by adding the other 4. I don't think we need to do that, but we can just as a double check. So 31.7 plus 24.1 plus 14.4 plus 5.5 plus 6.7 is 82.4. But again, faster to get there through subtraction. They both work, but try and go the fastest, most efficient way if possible. All right. So moving on to another definition, we're going to look at a random variable. And a random variable is a numerical measure of an outcome from a random experiment. And we often use a capital letter such as X to stand for the random variable. So for example, a while ago we were talking about rolling 2 dice and looking at the sum. One of the things you could do with a random variable is say let X be the sum when you roll 2 dice. And then if we happen to roll a 2 and a 5, we'd say X equals 7. If we happen to roll a 6 and a 3, we'd say X equals 9. But how you figure out X is not to solve an equation, it's to do the experiment, to roll the dice and see how it turns out. So that's how random variables are set up and how they work. So we'll look at an example of that on the next page. All right, so continuing on, here's that random variable example I promised. The number of days it took Chicago's Department of Streets and Sanitation to respond to requests to fix potholes are described by the density histogram shown. Let X equal the response time to fix a randomly selected reported pothole. So one of the things we need to remember about density histograms is that in a density histogram, the area of a bar, which they've labeled for us on most of these, is equal to the relative frequency for that category. So what they're giving us, they're calling density. It's really relative frequency, but relative frequency calculations are the same as probability calculations, so we can substitute them back and forth. And then I guess since these are areas, you could even say for density histogram, the area of the bars represents probability. And that idea that area can represent probability is really important as we move into stat class next semester. So it's good to kind of get used to it here. So find the probability that X is less than 7. So we just look at the graph, and this would be 0 to 7, so the area of that bar is 0.34. That's the relative frequency, but it's also the probability. So we're just looking at the histogram, trying to find the bars that match up with what they're describing, and then use their areas to get our probability. Determine the probability that X would be between 7 and 21, including the 7 because of the extra line, but not the 21. So on a histogram, the number that's on the edge of a bar is part of the bar to the right, not the bar to the left. So this 21 is not included in this 0.12, it's included in the 0.08 bar. So from 7 to 21 would be from here to there. So it looks like there's 2 bars that fall in that zone, and they have areas of 0.33 plus 0.12, and they're areas, right? And they're asking for probability, but remember, area on a density histogram is the same numerical calculation as probability. So we're going to use area of density histogram to answer probability questions. And then we have two of them, so we'll just add them together. So that's 0.45. All right, so now let's interpret those results in Word. I'll do both of them. This one is the probability that x is less than 7, but x is the response time to fix a randomly selected reported pothole. So if you found a pothole on your road and you lived in Chicago and you called in there, you would expect that there's about a 34% chance that they would take care of that in less than a week, right? In less than 7 days. So what would that be here? If you had a pothole on your road and you called in and asked for it to be fixed, there's about a 45% chance that it would take at least 7 days, but less than 21 days. So somewhere between about a week and almost 3 weeks. So interpretation, there is a 45% chance. When we talk about probability, we generally convert it back to a percentage, that it will take somewhere between 7 and 21 days until a randomly selected pothole that has been reported will be fixed, repaired, whichever word you want to use there. I guess cleaning this up a little, between 7 and 21 would not include the 7, so we should point out that this one is included. So from 71 to less than 21 days might be a little bit better way to say that, to match up with the or equal and the strictly less than. So I don't know, why not? We can fix it right here. Drag in a new color. It'll be somewhere from 7 to less than 21 days. I think that's a better fit for the symbols. The words that I had there between 7 and 21, those words are not inclusive. That would have been great if there was less than on both cases. So this is a little bit better. Let's try another one. Determine the probability that x would be greater than 42. So let's go look at our picture and think about where that would be. So x is greater than 42. Here's the 42. We want all of these bars right here. So we'd want to look at their areas and add them together. But they didn't give any of them to us, so we can't do it that way, right? But one of the things that we should know about a density histogram is that if you added the probability or area for all those bars, the total should be, think about it, it should be a 1, right? So if you want these missing ones, you could take the total of 1 and you could subtract all the stuff that you don't want. So we don't want any of these bars to the left, so if we subtracted all of them, the 0.34, the 0.33, the 0.12, the 0.08, the 0.03, and the 0.07, then if you subtract those away from the total, remember 1 is what you'd get if you added all the bars together. So if you subtract this away from the total, you should be left with these. So that's the approach we would have to use on that one. So let's see how that works out. So 1 minus the 0.34, the 0.33, the 0.12, and so on. And we get 0.03. I would just think about it real quick to see if that makes sense. That's a pretty low probability, but those are all very short bars, so that could be a reasonable answer to that, I think. So 1 minus 0.34, 33, and 12, and 08, and 03, and 07. Just double checking those all real quick against the bars. Looks like we did that right. And interpret that result in words. So we're talking about the probability of the time it takes to fix a pothole, and we're saying it's about a 3% chance. So kind of going off the model from right there. There is a 3% chance that it will take, let's see, this is the time it takes, more than 42 days. So it will take more than 42 days until a randomly selected pothole that has been reported will be repaired. and just our luck, that's probably the one on our street, right? It's not very likely that if you reported a pothole on your street in Chicago that it would take, I think that's 7 times 6. So that would be like 6 weeks, a month and a half to get that pothole reported. That doesn't happen too often, but 3% of the time when somebody reports that there's a pothole on their street, it can take that long. Kind of unusual, but it does happen. All right, so the key thing we want to remember from that problem is when we are working with a density histogram in a probability context, the area of the bars can be used to answer probability questions. And that idea that area and probability can be interchanged somewhat is a really key concept in statistics. We end up using that to answer lots of probability questions. Most of our probability questions in statistics get answered using area, so that's definitely something that you will see again.